Hey everyone, welcome to this explainer. Look, today we're diving straight into something that trips up a surprising number of plants. We're talking about pressure measurement. Now, treating pressure like it's just some simple throwaway concept, that is literally building a landmine right in the middle of your facility. Get the reference wrong and bam, that landmine goes off. So we're going to break down exactly how this happens, and more importantly, how to make sure your plant's data is actually telling you the truth. Let's get into it. Picture this. You've got a vibrating, reciprocating compressor skid. Day in and day out, that relentless mechanical vibration is just slowly, silently destroying your pressure transmitter's accuracy. And the crazy part? Nobody even notices the drift until the safety system nearly trips on a totally false reading. I mean, pressure sounds so simple, right? It's just a number on a dial. But if you get the reference wrong, or, say, you install the wrong technology in a harsh environment, you've built a landmine that will absolutely go off and cost you some serious downtime. So fundamentally, a pressure transmitter is just converting force per unit area into an electrical signal, usually giving your controller that standard 4 to 20 milliamp output. And yeah, sure, it supplies the primary process variable, or PV, for your basic pressure loops. But here's the kicker. It also secretly feeds a ton of your flow and level measurements too. We'll be looking at that throughout this explainer. Because honestly, the exact same physics used to measure pipe pressure are used to measure flow across an orifice plate, or even to calculate the liquid level in a massive storage tank.
All right, so let's explore the 3 critical references every process engineer absolutely needs to know to avoid those invisible landmines. Here is the golden rule. Pressure is never measured in isolation. It always, and I mean always, needs a reference point to compare against. Out in the field, the big 3 you're going to encounter are absolute, gauge, and differential.
First up, we've got absolute pressure. Now, this measurement always uses a perfect vacuum as its baseline reference point. So zero absolute literally means an environment completely devoid of matter. Zero atmospheric pressure pushing down on that sensor. And this is absolutely vital for processes operating under deep vacuums. If you didn't use absolute here, regular day-to-day atmospheric pressure changes would just totally wreck the accuracy of your data.
Next up is gauge pressure. This one is referenced against the local ambient atmospheric pressure right around the sensor. Frankly, this is what most of the instruments on your plant floor are actually reading. Think about it. If you have a pressure gauge just sitting disconnected on your workbench, what does it read? 0. Why? Well, because the pressure inside the sensing tube exactly matches the atmospheric pressure pushing on the outside of it.
And finally, we have differential pressure. Now, instead of relying on a vacuum or the atmosphere, this guy measures the exact difference between 2 specific user-supplied process points. You hook up a high-pressure port and a low-pressure port, and it measures the delta. Like I mentioned a minute ago, this is the absolute workhorse behind a massive chunk of flow and liquid-level measurements across the entire industry.
I love this next analogy because it brilliantly illustrates the difference between those first 2. Think of gauge pressure like measuring your height standing on the floor. Everyone in the room agrees the floor is the 0 point, right? It's highly practical. Absolute pressure, on the other hand, is like measuring your height starting all the way from the center of the Earth. Now, while measuring your height from the center of the Earth is technically true and scientifically absolute, it is totally useless for everyday comparison. I mean, unless everyone you're talking to shares that exact same reference point, it just doesn't work. The main takeaway here is that a pressure number without a stated reference is a completely meaningless number. You just have to know the baseline to know what the data is actually telling you.
Okay, so how do these numbers look out in the real world? Let's do a quick mental check. Imagine one of your operators looks at a monitor for a vacuum distillation column, and it's reading 50 millimeters of mercury absolute. What's the call here? Is there a wiring fault? Should they start panicking?
The answer is a definitive no. See, because 50 millimeters of mercury absolute is a measurement starting from a perfect vacuum. In everyday gauge terms, that's roughly 710 millimeters of mercury below local atmospheric pressure. So that column is actually pulling a heavy vacuum, and the whole system is working exactly as designed. But you can see how an operator who isn't familiar with these distinct reference points might see that positive 50 on the screen and panic, right? They might think the pressure is spiked right there on the plant floor when it's actually in a deep vacuum. They might even shut down a perfectly healthy process. And that is exactly why this foundational knowledge matters so much. Knowing your reference prevents unnecessary panic and keeps your process running safely.
What's really fascinating here is how just locking in these 3 references perfectly equips you to diagnose true plant issues rather than, chasing ghosts. Whether you're dealing with absolute for those delicate vacuum systems, gauge for your standard utility lines, or differential for flow rates across an orifice plate, you now have the exact mental framework you need to interpret that data correctly.
All right, now that we've got the references down, it's time to look ahead to part 2, where we cover the sensing technologies themselves. We're going to open these devices up and explore the internal components, things like strain gauges, capacitive sensors, and resonant wire, and really dig into the trade-offs between high accuracy and ruggedness.
But before we wrap up this explainer, I want to leave you with a bit of a provocative question to chew on. Which highly accurate sensing technology actually becomes a massive liability the second you bolt it onto a vibrating compressor skid? Think about how the physical environment quietly corrupts that control loop performance. We're going to answer exactly that in part 2. Thanks so much for joining me for this explainer, and stay curious.